Have you ever wanted the ability to power virtually anything on the go? Well, in this video, I will show you step by step how you can make a power bank that can do just that. With the ability to power at least 7 devices. This power bank also features a removable battery pack, which can be replaced for extra capacity. The capacity of the battery pack is 188 watt-hours, which is more than 5 times the capacity of a normal power bank. The 18650 batteries this power bank uses are easily found in things like old laptop batteries, so it is easy to get them for free or very cheap. And if you manage to do that, the total cost of the components goes down to $60, which is 2 times cheaper than anything commercially close. For the output, the power bank has a 150 watt wall port that can power anything from lights to fans, to mini fridges or even TVs. The power bank also has a DC port that is adjustable from 13 to 50 volts, that is made for devices that can accept DC directly, like laptops and some soldering irons. With a maximum power output of 120 watts, the power bank can power mid-range gaming laptops comfortably even at maximum load. Finally, the power bank also features 4 standard USB ports, with 2 having Quick Charge 3.0. And if you forget your cable, the power bank also has a wireless charging pad on the top. The power bank charges with a standard laptop charger, or USB-C. And optionally, the power bank also comes with RGB lighting, so it can look cool even in the dark. All this power comes in a size slightly larger than a standard water bottle, so it can be easily carried around. Furthermore, with overvoltage, overdischarge, short circuit, and over-temperature shutdown, along with a fully automatic cooling system, the power bank is very safe to use if built correctly. I will now show you the step-by-step process of building this power bank. Here are the timestamps for each step in this video. You can skip to any of those steps if you want, but for the rest of you, here we go. For this project, you will need a number of different components. As for always, all the links and part files are in the description. For the output, you will need a 12-volt USB quick charge car adapter. I have already taken it out of its case. A 200 watt boost converter, a 150 watt 12-volt inverter with 2 USB ports, and finally, a wireless charging circuit. You will also need a step-down DC converter with a constant current feature. This is for charging the batteries. And 2 more mini DC step-down converters. A 3S lithium-ion battery management circuit with balanced charging. The board also has overcurrent, overdischarge, and short-circuit protection. To switch the high currents, you will need this SRA 12-volt DC relays that can handle up to 20 amps. You will also need 2 5mm DC jacks, 60 by 10mm 12-volt fan, a Schottky diode that can handle at least 5 amps, a pair of XT60 connectors, a 20 amp car fuse, 7 of these 3 amp slide switches. If you want RGB on your power bank, you will also need 12-volt RGB strips and a 3-button controller. You will also need 22, 18, and 12 gauge wires, 2 mini voltmeters, 0.5 mm thick copper strips. All the screws used in this video are gonna be M3 flathead screws, 5mm aluminum heatsinks, various color 3mm LEDs. The temperature control and protection are done through these bimetal temperature switches. These switches open or close at their rated temperature. For this power bank, you will need 4 normally closed 45 degrees type and 3 normally open 45 degrees type. Most importantly, you will need 15 18650 batteries. You can use new or old cells as long as they satisfy these 3 conditions. 1. They have roughly the same tested capacity. 2. They have roughly the same internal resistance. 3. The maximum discharge current of each cell must be at least 5 amps. Finally, you will need to 3D print all the files in the description. Be aware that some components must be printed in PETG or ABS plastic. Here is the overall schematic of the power bank. It is separated into 7 systems. They are the battery pack, the charging circuit, the AC inverter, the DC step-up converter, the USB over temperature protection circuit, the wireless charging circuit, and finally the automatic cooling system with RGB. In the description, I also included the CAD assembly of this power bank. If you wonder how the power bank comes together, you can download the model and see for yourself. I also included the version without USB-C and the version without RGB. The first step to building this power bank is making the removable battery pack. To start, get the tested 15-18650 batteries. I am using the model NCR18650B for its high capacity, but if you want to bring this on a plane, use cells that are less than 1800 mAh, or use fewer cells in each parallel group. Measure each cell to make sure that they are at the same voltage. If not, charge or discharge the cells until all 15 cells have the same voltage. Now, get the 3D printed battery holder and insert the battery with the positive on the side and negative in the middle. This creates a configuration that looks like this. After all the batteries are inserted, press on the cap and secure it with 6 screws. Before the front 2 screws are secured, slide in the BMS like this. Now cut 4 strips of 0.5 mm thick copper sheet that is 7 mm wide. This is what's going to carry the large current from the batteries. You can also use brass or nickel strips if you have them. Bend and cut the copper strips to length. Now get your iron as hot as possible and tin the copper strips. Now solder the batteries to the copper strip. Make sure you never spend more than 3 seconds per solder connection, and only resolder after the joint cools down. When the soldering is done, the battery pack should look something like this. Solder the strips to the BMS. Next, solder short 12 gauge wire to XT60 connector, and place and solder the XT60 in the holder of the battery pack. Then glue the XT60 in place. Make sure that it is straight and flush with the surface. You can add a heatsink onto the MOSFETs, but this is optional. Now it's time to test the battery pack to make sure that it is safe to use. First, add a heatsink onto the converter, then connect it to the input of a power supply that is above 14 volts. Then connect the output to a meter that measures voltage and amperage. Adjust the output to 12.6 volts. Next, short the output so the converter goes into constant current mode, and then adjust the output anywhere between 2 to 3.5 amps, depending on how fast you like your batteries to get charged. Then, connect the output of the meter to the battery pack. The battery should begin charging as soon as the blue light turns on. Closely monitor the voltage and temperature of each cell. If there's a deviation of 0.2 volts, or a cell gets noticeably hotter than the other cells, stop the charging process immediately and check the soldering connection or replace the cell. When the light turns green, the charging process is finished. Now the second test is the discharge test. First, connect the battery to an input of an amp meter. Then, get something that uses 12 volts and draws a lot of power. In this case, I'm using my 100 watt flashlight. I made a video about how to make this flashlight. Check it out if you're interested. Anyways, put at least 10 amp load onto the battery for 20 minutes. During this time, closely monitor the voltage and temperature of the battery pack. Pay special attention to solder joints, as improper joints can heat up quite quickly. After repeating these 2 tests 2 more times, we can move on to making the locking mechanism. First, get the 3D printed parts and a hinge. Using the hinge, mount the pull tab onto the base. The hinges in this video are too small, so later on I switched them out for larger ones. Next, screw in the locking ring and add in the locking shims. Finally, add on the lid and screw the assembly onto the back of the battery pack. The battery pack is now complete. You can make as many of these battery packs as you want, as long as you have enough batteries. This way, if 188 watt-hours is not enough, you can just slide in another pack. The next step is to make the charging circuit. Here is the overall schematic, and this is how it works. When no power is connected, the current can flow through a normally closed contact of the relays and to the output. But when power is connected, the current flows through the step-down converter with constant current but then it is stopped at the relay. At the same time, current flows through the mini step-down converter. This turns on the cooling fan and the two relays. Now the current from the step-down converter with constant current can flow into the batteries. Now the output is switched off. This way the batteries are protected from being charged and discharged at the same time. First, we need to make additional modifications to the step-down converter. Desolder the screw terminals and the LEDs. Then, add a Schottky diode facing into the input. Next, solder thin wires to the LED pads. Now get the 3D printed base and screw in the step-down converter. Then, solder the input of the step-down converter to the 5mm DC jack. If you want to charge the power bank with USB-C, then you will need to buy a small USB-C 20V trigger and solder it in parallel with the DC jack. The next step is to solder 3mm green, red, and blue LED to the wires and test them to see if they still work. Then, mount them on the side in order from top to bottom of green, blue, then red. The next step is to get the mini step-down converter and adjust its output voltage to 12 volts. And then solder it to the DC jack. Now place two relays in this orientation. Solder a 45 degrees normally closed temperature switch in series with the input. This switch extends into the battery compartment. This way, if the battery gets too hot, the circuit automatically stops the charging process. Next, solder the two relay coils in series with the output of the mini step-down converter. Solder the output of the step-down converter to the normally open contacts of the relays. Then, solder a thick 12-gauge wire 90 degrees to a XT60 female connector. Then, solder on a 20-amp car fuse and wrap the contacts to insulate it. Solder a 12-gauge wire to the negative terminal. Attach the XT60 connector to the holder on the base. Solder the positive wire to both common contacts of the relay. Cut and tin the ground wire. Next, slide on a battery pack, connect it to power. The blue LED should light up as the battery begins charging. This indicates that the charging circuit is not complete. Now we can move on to the inverter circuit. First, take the inverter circuit out of its case and keep the screws because we will need it for later. Disconnect the 30mm fan and the outlet. Glue and solder the fan to the slot next to the mini step-down converter. If you remember the last power bank I made, you will remember that the inverter has heatsinks on the power MOSFETs. Well, that's not the case with this inverter, so we need to make our own heatsinks. I simply bent two pieces of copper sheets and thermal epoxied them onto small heatsinks. Then I thermal epoxied them onto the MOSFETs. On one of them, I attached a 45-degree normally open temperature switch. Also, by the way, wrap all thermal switches in tape because they are not isolated. And here's what the finished assembly looks like. Before adding in the inverter, sliding a relay into the base like this. Then, solder a 12-gauge wire across the three relays like this. Then, carefully slide in the inverter. Solder the positive input of the inverter to the normally open pin of the relay. Then solder the ground wire of the inverter to the ground wire of the XT60. Solder a switch to one of the coil pins of the relay, and solder the other coil pin to the ground. With this, the base is not finished. Now we can move on to the middle layer. First, unscrew the boost converter and take it out of its case. Then, desolder the screw terminals, the potentiometer, and the LED. Replace a small SMD LED with a 3mm one. And now use longer wires to extend the potentiometer. Solder a 18-gauge wire to the output. Then, slide in the boost converter onto the 3D printed middle layer and use a screw to secure it. Slide the potentiometer in this orientation into the middle layer. Then, get the 3D printed voltmeter and switch bracket. Add in a voltmeter and a switch, and solder them in series. Now, solder and glue a DC jack onto the output of the boost converter. Glue on the voltmeter and switch, and solder it in parallel with the output of the boost converter. Then, press in the relay in this orientation. Solder the normally open pin of the relay to the input of the boost converter. Then, solder a switch to one of the coil pins. Then get the 3D printed adjustment knob and insert a piece of 0.5mm copper sheet into it. Glue the stopper onto the other side and make sure the knob can spin freely. Carefully line up and glue the adjustment knob onto the middle layer. Now as the knob is turned, the potentiometer turns with it, and the voltage can be adjusted this way. Next, desolder the LEDs on the quick charge converter and replace it with a 3mm green LED. Then, desolder the contacts on the board. Cover the contacts on the back with Kapton tape, then thermal epoxy on small heatsinks, along with a normally open 45 degrees temperature switch. Okay, I have to stop the video right here, because I forgot to film a step, and that is to solder 2 wires to the positive and ground pin of the USB. These 2 wires are for the wireless charging circuit. Then, press and glue the USB assembly onto the board. Next, thermal epoxy on another normally open 45 degree thermal switch onto the heatsink of the boost converter. Then, solder the 2 thermal switches in parallel. Next, add another switch on top of the switch for the boost converter. Solder one switch wire to the positive of the USB converter and the other wire to the coil pin of the relay. By the end, you should have a pair of wires from the USB output, a pair of wires from the 2 thermal switches in parallel, and another pair of ground wires. Then, insert a 45 degree normally closed thermal switch to the bottom of the assembly. Before adding on the middle layer assembly, thermal epoxy a 45 degree normally open thermal switch next to the inverter relay, and solder the 2 thermal switches in parallel. Alright, it is time to put the 2 layers together. Carefully place on the middle assembly. Solder the 12 gauge output wire from the relays to the input of the relay on the middle layer, and attach the 2 ground wires to the ground wire of the XT60. The next step is the automatic cooling system. For this step, locate the 2 pairs of wires from the temperature switches. Solder one side of the parallel connection directly to the input of the relays. In other words, they are connected directly to the battery, so the cooling system would always stay active. Now, get the 60 by 10mm fan and optionally, another mini DC step-down converter. The purpose of this converter is to adjust the fan speed, since the 12-volt fan I have is too fast and noisy. For my case, I solder the output of the boost converter to the fan. Then, I solder the other pair of wires from the thermal switches onto the input of the step-down converter. Connect the step-down converter to ground. The next circuit is the relay power system and the USB converter circuit. This is the overall schematic. Basically, the current flows through the battery and passes through the relays. Then, the current passes through 2 45 degree normally closed thermal switches. Then the current can flow through 3 components in parallel. They are the inverter relay, the boost converter relay, and the USB converter. This is also the over-temperature protection system. If either of the thermal switches detects the temperature of above 45 degrees, no relays can be turned on, so the output of the power bank shuts off. First, solder the 45 degree normally closed thermal switch to the 12 gauge wire from the output. Then, connect the switch in series with the other normally closed thermal switch, which was mounted under the middle layer earlier in the video. Next, solder the output of the thermal switch in parallel with the USB converter switch, and with the 2 other relay coil pins that have not been used. Now, it is very important to test the circuit to make sure that all systems are working properly. First, connect 12 volts power to the XT60 connector and flip on all the switches. As you can see, all the output circuits turns on. Now, let's test the over temperature protection circuit. First, I set the temperature of my soldering iron to 100 degrees, then pressed it onto the normally closed thermal switch. After a few seconds, all the output turns off, and only turns on after the switch has cooled down. Now, I load each circuit to the maximum amount and wait to see if the cooling fan turns on. And indeed, the cooling fan does turn on. With all the testing done, you have just made it through the most complex part of the assembly. Now you can screw on the middle assembly onto the base with 5 screws. Then glue the cooling fan onto the side. The final part of the electronics assembly is the top layer. First, mount a voltmeter and switch onto the top assembly. Then connect them in series. Next, get the RGB controller and desolder the output connector. And then mount a small switch in this location. Then glue the RGB controller next to it and solder it in series with the switch. Then, solder the RGB controller in parallel with a voltmeter. Next, slide in the wireless charging circuit and glue it in place. Then, solder a switch in series with the wireless charging circuit's micro USB input. The next step is to solder the 4 control wires to the RGB controller and connect them to the cut up RGB strips on the back. Then, solder the breakout pins to the last RGB strip. I made 4 more RGB strips and connected them with wires in between, and mounted them in the grooves of the battery compartment. Next, we can put the top layer onto the assembly. Solder the RGB voltmeter system directly to the output of the batteries. Then, using a large heat shrink tubing, insulate the ground wire. Then, connect the wires from the USB output to the input of the wireless charging switch. Then, screw on the top lid with 4 screws. The next step is to attach the battery compartment. You should have the 2 thermal switches and the RGB cable sticking out of the back. Connect the RGB cable and slide on the battery compartment. And then, press the 2 thermal switches into the grooves. Secure the battery compartment in place with 8 screws. Slide in the battery to make sure everything lines up. The next step is to get the 3D printed I/O shield. The I/O shield was printed with 0.2mm nozzle with a filament swap, so it has 2 different colors. Fill the LED holes with hot glue to diffuse the light. Then, insert the AC outlet into the I/O shield and glue it in place. Next, glue the inverter switch next to the 2 USB ports. Then, connect the AC port to the inverter board. Screw in the I/O shield with screws salvaged from the inverter earlier in the video. Next, get your 3D printed sleeve. Slide in the assembly into the outer sleeve. Then secure it in place with screws on both ends. Glue the RGB controller cover on and add on the stickers. Finally, get the 3D printed end caps. I printed them out of Ninja Flex, so it is flexible and is able to absorb shocks and impacts. The cap is glued on with double-sided sticky tape. This way it can be removed if needed. And with that, the power bank is finally complete. Thank you very much for staying with me through the whole process. The power bank can be used for emergency backup power, for outdoor camping, or anytime you need portable power on the go. So that's it for this project. If you liked it, please give this video a like and consider subscribing to my channel for more DIY projects like this. I'll leave you with a montage of this power bank in all its RGB glory. And as for always, thanks for watching.